Colligative properties of solutions. Colligative properties are different from the properties of the pure solvent. For instance, boiling points and melting points can be altered. Another interesting thing about colligative properties is it doesn't matter what type of solute you have, it just matters the concentration of your solute particles. One common colligative property is vapor pressure lowering. This is when the presence of a non-volatile solute, like an ionic solute or a solid solute, the presence of that in solution reduces the vapor pressure of the solution versus that of pure water. So, you can look at the vapor pressure curve here. Here you have pure water. It's got a higher vapor pressure than a solution. And the solution here has a 1 molal concentration of particles. We'll talk about that in just a second. So, for instance, at a temperature of 100 degrees Celsius, this is the vapor pressure of the solution, and this is the vapor pressure of pure water. So it's lower. At a temperature of 0 degrees Celsius, the vapor pressure of the solution is also lower than the vapor pressure of pure water. And look at these numbers. 100.512, that's the boiling temperature of a 1 molal solution. And negative 1.86, that's the freezing temperature of that 1 molal solution. So a solution of a non-volatile solute in a liquid solvent will always have a higher boiling temperature than the pure solvent. And you can calculate the change in boiling temperature by just using this equation. Delta T, the change in boiling temperature, equals Kb, that's the boiling point elevation constant, 0.512 degrees Celsius per molal, times the molality, times X. Now, what is X? X is the number of particles on the right-hand side of the solution equation. So for instance, here's the solution equation for sodium chloride. We put it in water and we get a sodium ion and a chloride ion. One cation and one anion, that means X equals 2. Say we were talking about magnesium chloride. Well, we're going to get an Mg2 plus ion and 2 chloride ions. One cation and 2 anions, that's 3 particles total, so X equals 3. So here's an exercise. Calculate the boiling temperature of a solution made by dissolving 50 grams of MgCl2 in 100 grams of water. So, first you're going to have to find the molality. That's going to be moles of MgCl2 over kilograms of water. And then you're going to use the Kb value and the X value in this equation to find delta T. Delta TB equals Kb mx. And then you're going to use the equation boiling temperature equals normal boiling temperature plus delta TB. where the normal boiling temperature of pure water is 100.0 degrees C. Pause your video and work it out. Then unpause to see the solution. So if you're ready, here is how to answer this question. The molality equals, let's see, moles over kilograms. So let's find moles first. So that's 50.0 grams of MgCl2 divided by the molar mass, which is 95.216 grams, which gives us 0.525 moles. So our molality equals 0.525 moles over kilograms water. And to get kilograms of water, we just take the 100 grams times 1 kilogram over 10 to the third grams, and that's 0.100 kilograms. And so we get 5.25 molal. So now we find delta TB. That equals 0.512 degrees Celsius per molal times 5.25 molal times X. And as you saw earlier, X equals 3. Right, so this is KB, this is M, and this is X. And we get 8.06 degrees Celsius. So that means our new boiling temperature of the solution is 100 degrees Celsius plus 8.06 degrees Celsius, which gives us 108.1 degrees Celsius. And that's because we take it to the tenths place because of our, let's just go with, we can do 108.06 degrees C. Is that what you got? Freezing point depression is calculated in a very similar way to boiling point elevation. So here's another exercise. What is the freezing temperature of the 5.25 molal solution created in the previous exercise by dissolving 50 grams of magnesium chloride in 100 grams of water? Go ahead and pause the video while you work. So here's the answer. Hit pause unless you're ready. So, first we find delta TF. That equals KFMX. KF is 1.86 degrees C per molal. So we have 1.86 degrees C per molal times 5.25 molal times X, which is 3. And we get 29.3 degrees Celsius. Now we use the freezing temperature equals the normal freezing temperature of the water, that's 0.0 degrees Celsius, minus the delta TF. Minus because this is freezing point depression. So 0.000 degrees Celsius minus 29.3 degrees Celsius equals negative 29.3 degrees Celsius. So a solution of magnesium chloride that is 5.25 molal, will be liquid all the way down to negative 29 degrees, way beyond the point where pure water would have frozen solid.